Welcome to all. Today we will discuss types of relation. In earlier video, we have discussed about Cartesian product and relation. Cartesian product will contain a set of all possible order pairs will be there in Cartesian product. Relation, how we have defined, we'll take some order pairs. So relation, we can tell it as subset of Cartesian product. Okay, 1 second. Next, see, we'll do presentation for types of relation. 1 second. Here we want to do presentation, but sorry. Okay. See, first one we will discuss about reflexive relation. In reflexive, see, first we told relation is subset of Cartesian product. Here R is a relation in set A. Then we'll discuss. Then R will be subset of A cross A. A cross A will contain all order pairs. Okay. Then we'll discuss all we can discuss all these types of relation. We'll discuss in set R is relation in A itself, not from A to B. This reflexive, symmetric, and transitive relation. Reflexive relation, how we will define? R is reflexive if and only if for every A belongs to A. If you take any element in the set A, then A comma A will be there in the relation. That means A is related to A itself. We have given so many examples, see. Okay. Here first example what I have given, this R1 you take. It is containing order pairs like 1, 1, 1, 2, 1, 3, 2, 2, 2, 3, 3, 3. And A set A, how you have defined, you have taken only 3 elements, 1, 2, 3 elements. And here if you see the relation, how the relation is, see, X, the first coordinate is less than second coordinate, see. X is less than or equal to Y, like that we can tell. Okay. In such relation, see, you are having 1, 1 and 2, 2 and 3, 3 are there. Okay, this element, this, see, if you take 1 in set A, 1, 1 is there. 1 is related to 1 and 2 is related to 2 and 3 is related to this. All order pairs are there in the relation. Then R is reflexive. Okay, R is reflexive. Like that we can tell. Okay, 1 minute, ma. I'm unable to use my mouse. Okay, then I have to stop this, I think. Then I can use my mouse. I will show the presentation also. Animation like that, it will come. Reflexive we told. Now we'll give some examples. Here, R we have taken is less than or equal to we have taken. Is less than or equal to in relation, we are having all order pairs, see. Okay, 1, 1, 2, 2, 3, 3, all are there. So we can tell that R is reflexive. One non-example we'll take. Here, see. In set A, B, C elements are there. If you take A is related to A, order pair is there, A comma A order pair is there, no issue. If you take B, B comma B is there, B is related to B, no problem. If you take C comma C, is C comma C is there in this relation? See all, check all the order pairs. C comma C is not there in the relation. This symbol, no, what you will call this symbol? Does not belongs to C. This symbol is called does not belongs to. C comma C. When you take C element in A, C is not related to C. C comma C order pair is not there in the relation. Therefore, this R is not reflexive. R is not reflexive. Next, in geometry, if you take some set of lines in a plane, if you take, and you will define the relation as is parallel to. See, every line is parallel to itself, no? Therefore, is parallel to is reflexive. In geometry, if you take the relation as is perpendicular to, Okay, every line is not perpendicular to itself, so it is not reflexive. E is factor of you take. Every number is factor of itself, therefore E is factor of is reflexive. And E is subset also. Okay, E is subset. Every set is subset of itself. So E subset is also reflexive. And see, in each slide we'll learn something extra. What extra means? Here you learn identity relation. See, identity relation, it is also one type of relation in which every element is related to itself. If you take 1 comma 1 will be there. If you take 2 comma 2 will be there, and 3 comma 3 will be there. See, here I have defined a relation I, 1 comma 1, 2 comma 2, 3 comma 3 are there, and I told all identity relations are reflexive. See, in identity relation, if you take any element -1 comma 1 should be there in identity relation. Like that it is. All identity relations are reflexive. But all reflexive relations are not identity. Here, if you take the first example, R equal to 1 comma 1, 2 comma 2, 3 comma 3 are there. And some more elements are there. See, 1 comma 2. This is not a identity. This is not a identity relation. If you take 1 comma 2, you should have only elements which is related to itself. Okay, so that's why we are saying all identity relations are reflexive relation, but all reflexive relations are not identity relation. Next, we'll go for symmetric relations. A symmetric relation, how it is defined means, if you take some two elements, A comma B, you'll take. If A comma B is there in relation, then B comma A should be there in relation. That means if A is related to B, then B is related to A. Okay. If A is related to B, it implies B is related to A. Then only we'll say that it is a symmetric relation. Okay, we'll tell some examples. In real life, if you take in family relation containing only girl children, if you define each sister of that is symmetric relationship. An example also I'll tell. I took Veena is sister of Lina. Then what you'll say? Lina is also, you can say also Lina is sister of Veena. Some relations are there that you cannot consider as symmetric, like is father of. I'll give one example. Rama is father of Kusha. Then you can't say Kusha is father of Rama. That's therefore that is father of relation is not symmetric. Okay. Some numerical examples I'll give. Here see, order pairs I have taken. A comma A is related to B. You check A comma A B is there means you have to see B. See here B comma A is there, not a check. B comma A is also there. And if you take another B comma C is there, then sorry A comma C, A comma C is here, then C comma A is also there in relation means okay. If I take B comma C, I have to check C comma B is there or not. It is also there. Therefore, all symmetric relations are there. Symmetric order pairs are there. Therefore, what you can say? This is a symmetric relation. In last slide, is less than or equal to relation I have taken. Whether it is symmetric or not, I'll check now. If you take 1 comma 2, 1 comma 2 is there here in this. 2 comma 1 is there, you check. It is not there in this relation. So 2 comma 1 does not belongs to R. When 1 is related to 2, 2 is not related to 1. Therefore, it is not symmetric relation. Next, E is perpendicular C, we'll see. If you take set of lines in a plane, if L is perpendicular to M, then you can say M is perpendicular to L. Perpendicular means the angle between the two lines is 90 degrees. If L is perpendicular to M, M is perpendicular to L. Therefore, E is perpendicular to E is symmetric relation. See, for symmetric relation, I am giving one hint like that. What is that hint means? If you see R and R inverse we told, you have to interchange X and Y coordinates, first and second coordinates. And R inverse you compare. If they are equal, then it is that relation is symmetric. See, this is a short way to identify whether it is symmetric relation or not. Okay. Next, E subset of we'll see. If A is subset of B is subset of A or not, we'll check. I have given, see, I took natural numbers, whole numbers and all. Because number system we know. All natural numbers are whole numbers. So natural numbers is subset of whole numbers. But all whole numbers are natural numbers? No. Why? Because 0 is only whole number, but it is not natural number. So if n is subset of W, we can't say W is subset of n. It is, therefore it is not symmetric relation. And some exceptional cases will be there. When A is subset to B and B is subset to A, it is possible only when A equal to BC. And this is the fundamental property of sets. Using this, we'll prove many many results in sets. Okay, and this relation is having some name. See, when this is possible, when A is subset to B and B is subset to A, when A and B are equal, no, this relation is called anti-symmetric relation. These are the extra things you will learn in this slide. Now transitive relation will come. Transitive relation, unknowingly you are using C. Now we'll tell that relation is transitive. Some three elements you take, A, comma, B, comma, C in relation you take. If the order pairs like A, comma, B is in relation and B, comma, C is in relation, then A is relation to C we have to write, sorry here. Here A is relation to C we have to write. 1 minute. That correction I have to do. Okay. Drawing. Here this is AC, not okay. That is A is related to C you have to write. I can take pen is there. Okay. A is related to C, we have to see. Here see. A is related to B is related to C means we have to show that A is related to C, we have to show. Okay. I'll come back to the presentation better. I'll discuss some more, many examples, then you will come to know what is E is less than or equal to. From first slide onwards, we are telling the same relation. Okay. That I am discussing here. E is less than or is transitive or not, we'll discuss. For 1 comma 2 is there and 2 comma 3 are order 1 comma 2 is there and 2 comma 3 is there, then 1 is related to 2 and 2 is related to 3, then 1 should be related to 3. 1 comma 3 is there or not, you check. 1 comma 3 is there, no? Therefore is less than or equal to is transitive relation. When 1 is less than 2 and 2 is less than 3, obviously 1 will be less than 3. Unknowingly you are using transitive relation. One example here, one more non-example I am taking. This side non-example I am telling. A comma B is related to R. B comma C is related to R. Whether A comma C is there in relation or not, you check. You check all the order pairs. No, we are not having A comma C. A comma C does not belongs to R. Okay. Therefore, it is not transitive relation. Now, only in reflexive you told for every. Here for any you are telling. That means uh, no need of all elements should satisfy that condition, not like that. Here if you see C comma B is there, C comma B is there and B comma A is there. Okay, then here see C comma B is there and B comma A is there. Then C comma A is there, see. C comma A is there. Then you can't say that that is to satisfy transitive property. Okay, for any you told. For any if A is related to B and B is related to A, then A should be related to C, you have to say. That's it. Then it's a transitive relation. Some more example will tell, then it will be more clear. See. E similar concepts we are discussing in 10th class. That is also transitive relation. One regular example I'll take. One triangle ABC, right angle at C I will take. Okay, I will draw CP perpendicular to AB I will draw. Okay, perpendicular I am drawing from the vertices of a right angle triangle. Okay, then here see, if I take angle, this is theta, then already here 90 degrees, APC is 90 degrees. The remaining two angles will be complementary angle. One angle is theta means another angle is 90 minus theta. Here angle C is 90. So one angle is 90 minus theta means other angle is theta. Therefore, the other remaining angle will be 90 minus theta. Okay, if you draw perpendicular from the vertices of a right angle triangle, the two triangles formed are similar to the whole triangle. See, that ACP triangle, if you see here ACP triangle, this triangle is similar to whole triangle because in all the triangles you are having 90 degrees, theta and 90 minus theta is there. If corresponding angles are equal, they are similar. And another triangles, this one, CPB, that is similar to whole triangle. Okay, these two triangles are similar to the whole triangle. Then what you can say? This triangle is similar to whole triangle. This triangle is similar to whole triangle. Then they are similar to each other, no? This we have wrote. How means by transitive property. There you are using transitive property C. One non-example is perpendicular, I will say. Three lines in a plane I am taking. If L is, I will show the animation, see. Then you will understand much better. Here, see, I am taking some line L. And M perpendicular to L I am taking. L is perpendicular to M I took. Then some other line I will take N line. That is also perpendicular to M I will take. Then can you say L and N are perpendicular? No. L is not perpendicular to N. Here clear it is, very clear it is there. See, here 90 degrees, here 90 degrees. A pair of corresponding angles are equal. Then the lines are parallel. L and N are parallel, not perpendicular. See. E is perpendicular to is not transitive. See, clear no? Very clear no? And E subset I will discuss. I will discuss in number system I will discuss. Okay, I will take Z set of sets I will take in relation. Natural numbers are subset of whole numbers. Whole numbers are subset of integers. Then what you can say? Natural numbers are subset of integers we can say no? So therefore E subset of is transitive relation. Now we'll discuss about equivalence relation. Okay, R is equivalence if and only if it satisfies if R is reflexive, R is symmetric, and R is transitive. All three it has to satisfy. Okay, let's discuss one example very clearly. E is parallel to relation you have seen. Every line is parallel to itself. Therefore, R is reflexive. If L is parallel to M is parallel to L. Therefore, E is parallel to is symmetric. If you take three lines, if L is parallel to M and M is parallel to N, then L is parallel to N. If two lines are parallel to the same line, then they are parallel to each other. Therefore, R is transitive. Therefore, E is parallel to what you can say? It is a equivalence relation. Why? Because it is reflexive, it is symmetric, and it is transitive. One more example, E is less than I will take. That I told. It is a relation in A. See, relation means it is Cartesian product of A cross A, no? We'll take some elements from A cross A. Here, if you see 1, 1, 2, 2, if you take any elements in set A, the element is related to itself, therefore R is reflexive, you can say. But if you take 1 is related to 2, if you say 1 is less than 2, but 2 is less than 1, we can't say. Therefore, 2, 1 is not related to 1. 2 is not related to 1. Therefore, it is not symmetric. But we have seen it is transitive. When 1 is less than 2 and 2 is less than 3, 1 will be less than 3. It is transitive. It is reflexive and transitive but not symmetric. Therefore, we can't say it is equivalence relation. It is not an equivalence relation. In this slide, what extra you learn, which will be there, which will not be there in your textbooks. That note I have written. See, if you take some relation, smallest equivalence relation, if you want, that how you can do some relation R1 you see. If it contains 1, 1, 2, 2, 3, 3, it is smallest equivalence relation. See, it will satisfy reflexive, symmetric, and transitive property. Okay, the smallest equivalence relation in set A is the relation of equality in A, in R, in A, sorry. E is equal to relation. is the smallest equivalence relation. It will satisfy all the three properties. And what is the largest equivalence relation? If you say, if you that relation contains all the order pairs of A cross A are equal to A cross A, if you take, then that will be the largest equivalency. This A cross A will satisfy all property. It will be reflexive, it will be symmetric, and it will be transitive also. See, okay, in A. So largest equivalence relation is A cross A. Okay. Next, some more relation we'll discuss. That is, empty sets are there. The set with no elements is called empty set. If uh, if no element of A is related to any element of A, that in that relation elements are not there. That empty set you can denote with this symbol C, this pi. That means it has no elements. And pi is subset of Cartesian product C. This such relations are called empty relation. Next, if you take A cross A, it will contain all order pairs. Therefore, what you can say, that relation is universal relation. Why it is universal relation? Means any relation you take, you have to take from here only, no? A cross A only, no? Therefore, this under consideration, this can be considered as universal relation. One more thing is partial order relation, which will be not there in your textbooks. When we can say that it is partial order relation means if R is reflexive, anti-symmetric, and transitive, then we'll say that it is partial order relation. E is subset of, you have seen. Every set is subset of itself. Therefore, it is reflexive. If A is subset of B and B is subset of A, it is possible only when A equal to B. Therefore, E subset is anti-symmetric relation, we told. And it is transitive also. A is subset of B and B is subset of C means then A will be subset of C. Therefore, it is transitive relation. It is reflexive, anti-symmetric, and transitive. Therefore, it is a partial order relation. Is less than or equal to also partial order relation. See, one more example we'll tell, which is very helpful. That is E's factor of, we'll discuss. N set of natural numbers you are taking. E's factor of. When you will say it is factor, it will divide the other number exactly. Then we'll say it is factor. Every number is factor of itself. Therefore, it is reflexive. And if you take x divides y, x is factor of y and y is factor of x. This is possible only when both are equal. Therefore, x divides y and y divides x means it is possible only when x and y are equal. Therefore, it is anti-symmetric relation. If x is factor of y, y is factor of z, then x is factor of z. This will tell in detail. See here. When x is factor, y you can write it as multiple of x, no? Y equal to nx, some natural number. And z, you told y is factor of z, then z you can write it as my. Okay, now you have to show that x is factor of z. That means z equal to some multiple of x you have to show. First you write z equal to my you are having. It's the y, what you can write, nx you can write. Y place I am writing nx. So what I got? Z equal to, I got m into n times x. Some product of x. So x is factor of z. X will divide z, no? You can take some numbers and you can tell these. Okay, hence the relation is transitive. Therefore, this is also a partial order relation. Is factor of is a partial order relation. Now we'll come to the last slide, that is special relation. By seeing this picture, you will come to know what relation I am going to talk. Relation between child and mother, that is very special. See. Not like other relations, sister, brother, and all. This is blood relation. It is very special. Okay, in relations also we are having some special relation. How? If F is a relation from set A to set B, here two sets, set of elements we are taking. Okay, and for every A belongs to A, some first, if you take some element in first set, there that will have unique relation with some element in the B. Okay, unique relation. See here, unique word you have to key, it is key. Unique B belongs to B. Every element in A will have unique relation with the element in B. Then only we'll say this is a special relation, and it is also called function C. Function is a very big, vast concept. Okay. F is said to be function from here, see, from A into B. And you can write like this. F maps A to B, we can say. Okay, we can also say F maps A to B. We'll give some examples, then the concept, examples and non-examples, then we'll discuss, then the concepts will be very clear. I'm showing the animation. See, set A, I'm taking three elements. Set B, I've taken two elements. Here one relation, F1 I'm defining like this. 1 comma A is order pair, 1 is related to A, 2 is related to B, 3 is related to B I'm taking. See, each and every element is having unique relation. No? Here, see, this B, it is having relation with 2 and 3. We are not bothered about the elements in the second set. We are bothered about the elements in the first set only. One non-example I will discuss. See. Okay, here F3 is some relation. 1 is related to A, 2 is related to B, and 3 is not related to any element. It can't be a function. You told for every A belongs to A. So every element should have unique relations. Here this element 3 is not having any relation. Therefore it can't be a function. One more example we'll discuss. Here see. Here 1 is related to A, 2 is related to A, 3 is related to A. This is a function C. Here in second set, if some element is not having relation, we do not have problem. Each and every element in first set should have unique relation. Okay. That's why we told child and mother relation. See, here all these children are belongs to one mother. And this mother is not having any child. No problem, it is function. One more non-example we'll discuss. Here see. 1 is related to A, 2 is related to A, 2 is related to B also, 3 is related to B. Here this is not function. This F4 is not function. Why? Here we are having problem with this. This child will born to two mothers. It is not possible. To have impact, I can tell this. See here no child cannot be, see without mother no child can be born. No? Even though I can tell to give some impact, I will tell some dialogue. Uh, if you see Balakrishna cinemas in Telugu cinema, legend one cinema is there. In that he will tell. His dialogue king. See, he will tell like this. Even gods must be born from mother womb. Even he is God, he has to come from mother womb only, no? So here, this 3 is not having mother. It is without mother, how a child can be born? So this is not a function. Okay. See, I related with a child and mother. Function, how, when it is function means the relation between child and mother. Here, these two fellows are children of this mother. Okay. Child function, special relation, no? I have linked with real life, child and mother relation like that. Okay, I hope it is very clear.